When looking at the proton NMR spectra of ethanol, the first thing you want to do is draw your structure. Once you have drawn your structure, you want to determine the equivalent carbons. Starting from the left carbon, there are 3 equivalent hydrogens attached to that. Our next carbon has 2 equivalent hydrogens attached to that, and our oxygen has 1 hydrogen attached to that. Next, we need to determine the splitting patterns of our 3 different groups. From this, we know there are 3 signals to look at in our proton NMR. When determining your splitting patterns, you look to the adjacent carbon, and the number of hydrogens is how many splits you will have. So for the first one on the left, we have 3 hydrogens, and the adjacent carbon has 2 hydrogens, which means there will be 2 splits. Shown in a 1:2:1 ratio, or Pascal's triangle. Next, we will look at our adjacent carbon, which has 2 hydrogens attached to it, and instead of looking at the oxygen with 1 hydrogen attached, you only look at the carbons. So we will go back to the carbon with 3 equivalent hydrogens, which means there will be 3 splits. Lastly, our oxygen with 1 hydrogen attached will not have any splitting. Now that we have determined all of our splitting patterns, we can go back and look at our proton NMR of ethanol. And the 3 hydrogen, as we know, has 2 splits in a 1:2:1 ratio right there. Our 2 hydrogens has 3 splits, and that was in a 1:3:3:1 ratio. And lastly, our 1 hydrogen with no splits is the most downfield because of deshielding. Since deshielding is a reduction in shielding, which means it'd be more downfield because it is less stable compared to our other 2 signals. Also, we have our integrated area, which corresponds to the 3 hydrogen right here, and our 2 hydrogen right here. And this integration area corresponds to the area underneath the NMR peaks. When looking at the proton NMR structure of ethyl acetate, the first step we want to do is draw the structure. As shown below is the structure of ethyl acetate. Next, we want to determine the number of signals, which is the number of different types of hydrogen atoms. So our carbon on the right has 3 hydrogen atoms attached to it, and the adjacent carbon to the left has 2 hydrogen atoms attached to it, so n equals 2. So we know that n equals 2 plus 1 equals 3. So this carbon is a triplet. As shown right here. So n equals 2, which means there are 2 splits. And it is a triplet. Next, we look at our carbon to the left, which has 2 hydrogens, and the adjacent carbon has 3 hydrogens, so 3 splits. N plus 1 equals 3. So this carbon is a quartet. Lastly, the carbon on the left has no adjacent hydrogen atoms, which means it's a singlet. When determining our peaks of the NMR, as shown above, the carbons furthest away from the double-bonded oxygen will be more stable and most upfield. In this case, that would be our triplet, which is about 1.3. And then our quartet, which is adjacent to an oxygen, will be the least stable and most downfield, as shown right here at about 4.2. When looking at the proton NMR, aspirin has a more complicated structure with a carboxylic group and ester functional group. First, we want to determine the number of signals, which is the number of different types of hydrogen atoms. We can see that there are 6 signals in aspirin. 1, 2, 3, 4, 5, and 6. Our 3H hydrogen right here in our ester functional group does not have any adjacent carbons, so we know this is a singlet. Our 1H hydrogen in our carboxylic group right here also has no adjacent carbons, so that is a singlet. We know that this hydrogen in the carboxylic group is going to be most downfield because it is bonded to the oxygen. And for our 3H singlet, we know that is going to be the most upfield because it is bonded to a carbon, as shown right here.